Hello, and welcome to the video accompaniment for Chapter 5, Section 2. In this video, we'll be talking about equivalence relations, a special kind of relation. In this video, and by the end of it, I'd like you to be able to determine if a relation is an equivalence relation, and to understand how and why an equivalence relation generates a partition. Now, this is sort of the special property of an equivalence relation. This is why we have this word in the first place and why we have these three properties. Because when it satisfies those three properties, it generates a partition and this will be very helpful for us as we move forward. All right, let's get into it. We'll start with just the definition. So a relation that satisfies all of these three properties, reflexive, symmetric, and transitive properties, is called an equivalence relation. So we'll start with an example here. So we're given this set S, the integers between 1 and 6 inclusive, and we'll define the relation R on S by just listing the elements of the relation. So here we have this relation. Those are all the elements that are related to one another. Let's tell, how can we tell if R is an equivalence relation? Well, let's check all three properties: reflexive, symmetric, and transitive properties. Let's check all of those and see if it meets them. If it meets them all, then it's an equivalence relation. If it doesn't satisfy one of those, then it's not. So reflexive. So ask yourself, is every element of S related to itself? And actually, I listed these out in kind of a helpful way. Notice we have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. And that's all the elements. So, yep, every element is related to itself. So for symmetric, we want to check each pair of elements for which A is related to B, and we need to make sure that B is also related to A in those cases. Now this is going to be pretty easy with these sorts of pairs where they're related to themselves, because if one's related to one, I also would need to check then that one is related to one. But of course it is, I just said that. And so we don't really have to check any of the pairs where an element is related to itself. We do need to check the rest of these though. So 1 is related to 4. So I need to check now that 4 is related to 1. And it is. I can find that right there. 4 is also related to 1. 2 is related to 3, so I better see, if it is symmetric, 3 better be related to 2. And it is. We'll keep going. 2 is related to 6, and 6 is related to 2. And let's see, we only have one other pair to check. 3 is related to 6, and 6 is related to 3. And so for every pair, every relation between elements in here, if A is related to B, then B is related to A. And so this is symmetric. For transitive, remember this has to deal with triples. This is if A is related to B and B is related to C, then A is related to C. So this is a little bit harder to check, but nevertheless, let's go through it. So here, 1 is related to 4. And what else is 4 related to? So I need to check triples such that A is related to B and B is related to C. And then once I've found those, I need to check that A is related to C in that case. So 1 is related to 4 and 4 is related to 1. So now I need to check, is 1 related to 1? It is. So that checks out. Similarly, here we have 2 related to 3. I need to check any other time that 3 is related to something. So where else is 3 related to something? Well, 3 is related to 2. And so there I can check if 2 is related to 3 and 3 is related to 2. Is 2 related to 2? Yep, it is. There it is. Notice I'd also have to check, so 2 is related to 3 and 3 is related to 3. Of course, 2 is related to 3, and so that checks out. So I don't really need to concern myself with these, again, with these pairs where the element is related to itself. However, it does mean that a lot of these are transitive by including those. All right. We have 2 related to 6, so I need to check all the pairs where 6 occurs as the first element of the ordered pair. So 2 related to 6. Where else do I have 6? I have 6 related to 6, but of course that'll check out. I also have 6 related to 2, and so I need to check, is 2 related to 2? Yes, it is. And so we can keep running through all these, and we'll see that anytime A is related to B, and B is related to C, that A is related to C. And so this relation is transitive. And so what we have here is an equivalence relation. And this means something special is going to happen. So let's check that out on the next slide. When we do have an equivalence relation, that is when we've checked our relation and made sure that it's symmetric, transitive, and reflexive, then we can define something called an equivalence class. So hopefully you've already read through the section and know what you've seen the definition for an equivalence class. I'll state the definition here in maybe a little bit different of wording. So let R be a relation on the set S, then the equivalence class containing the element A, equivalence class containing A, is the set of all elements of S that are related to A, or that A is related to. Of course, since it's symmetric, those two things have the same meaning, related to, in both directions. And this is denoted, this set is denoted bracket A. So let's take a look at an example of this. Let's find the equivalence class. Here's the same relation I had on the previous example, and we should be able to pick out now the equivalence classes. So let's just go element by element and pick out what are all the elements that are related to each one. So bracket 1 is the set of all elements related to 1. So what I can do here is I can look at all of my ordered pairs. If I have them listed out like this, I can look at all of my ordered pairs and look for when the first coordinate is 1. 1, 1, 1, 4. Any other times the first coordinate is 1? Nope. And then the equivalence class containing 1 is the set of all these guys that 1 is related to. So in this case, 1 is related, 1 is related to itself, so 1 is in there. That'll always be true because it's reflexive, hence the wording equivalence class containing 1. And then 1 is also related to 4, and so 4 is in that equivalence class. How about the equivalence class containing 2? So here I'll look at all of the places that 2 shows up in the first coordinate. So 2 is there, 2 is there, 2 is there. Anywhere else 2 shows up? I don't think so. And then I'll collect. So 2 will be in there, 3 will be in there, and 6 will be in there. So that was 2, 3, and 6 are all in the equivalence class containing 2. All right, let's figure out equivalence class containing 3. So everywhere 3 shows up the first coordinate. So I know 3 is related to itself. I know 3 is related to 2, which shouldn't be any surprise, right? This is an equivalence relation. So if 2 is related to 3, which we set up here, then 3 should be related to 2. And then we also have 3, 6 is an ordered pair, and so 6. So notice that these two equivalence classes are the same. The equivalence class containing 2 is the same as the equivalence class containing 3. Why is that? Well, that's because 3 showed up in that equivalence class containing 2. So any element that's in this equivalence class, its own equivalence class will be the same. This is sort of a special property here. So let's just keep going through these. 4. So everywhere 4 shows up, I know 4 is related to itself since it's reflexive. 4 is also related to 1. And that appears to be it. So we're seeing the same thing. Look, in the equivalence class containing 1, the element 4 was in there. And now the equivalence class containing 4 is the same thing. Those two sets are equal. And that's because they're in each other's equivalence class. Equivalence class containing 5. Well, we know 5 is in there. Is 5 related to anything else? Nope, 5's just by itself. And finally, the equivalence class containing 6. If our conjecture is right that anytime an element shows up in equivalence class, then the equivalence class of that element will be the same as that one we were looking at, we should get 2, 3, and 6. And in fact, we do. So all 3 of these guys are the same. Both of these ones are the same. And then 5 is sort of by itself. And so when we just collect the distinct equivalence classes, we could take a representative from each one of those. So now look at what happens. So we've already found the equivalence classes. Good, we did that. Check. Nice. I just want to explore a little bit here. Check what happens when I collect all the distinct equivalence classes. So I'll say consider the set P of all distinct equivalence classes. So P here, we could write it as equivalence class containing 1, equivalence class containing 2, and the equivalence class containing 5. Those are all the distinct equivalence classes. We could have written this differently, right? Because we know the equivalence class containing 1 is the same as the equivalence class containing 4. So we could have, say, written equivalence class containing 4 here instead of equivalence class containing 1. It doesn't matter. Let's expand those out now that we know what the equivalence classes are. So equivalence class containing 1 is 1, 4. Equivalence class containing 2 are the elements 2, 3, and 6. And then the equivalence class containing 5, that's just the set containing 5. So here P is a set of sets, right? Because it's a set of equivalence classes, and each equivalence class is a set. But do you notice a special property about this set of sets? Each set in the set, each pair of sets is disjoint. It's a pairwise disjoint collection of sets. Each is non-empty, right? I don't see the empty set anywhere here. And every element of S shows up in one of the sets. So the union of these 3 sets gives me all of S. And so the big realization here is that P is a partition. That when we take all the distinct equivalence classes, what we really get out is a partition of the original set. Now, it certainly worked here. We'd like to know, is this always going to be the case every time we have a relation on a set S? That is, every time we have an equivalence relation on a set S, does that necessarily give us a partition by collecting all the distinct equivalence classes? That's going to turn out to be true, and we'll see why that's true in a second. And it has to deal with these 3 properties that define an equivalence class, that those are really there to guarantee that it's a partition. And so that's sort of the special property here. Let's take a look at another example of an equivalence relation. So let's look at one more example of an equivalence relation. This is a relation on the natural numbers cross the natural numbers. So that is, this relation goes from the natural numbers cross the natural numbers. Natural numbers cross the natural numbers to the natural numbers cross the natural numbers. So An element of this relation will look like an ordered pair of ordered pairs. So that is, an element of this relation might look like AB, CD, something like this. So it's an ordered pair of ordered pairs. And that's kind of confusing, but maybe it helps to just think about when one ordered pair is related to another ordered pair. So here's our rule for defining when one ordered pair is related to another ordered pair, and that's if the first coordinate times the second coordinate is equal to the second coordinate of the first pair times the first coordinate of the second pair. So this seems really contrived and weird. Why would we want to consider this relation? This seems like a problem a teacher would give to their students just to mess with them because it seems so, convoluted. But actually, this is a really important relation. So that's why I just have consider here, because I want to talk about this relation for a second. And specifically, it's a relationship to rational numbers. And I'll just think of positive rational numbers. So notice for every positive rational number, A over B, we can associate an ordered pair of natural numbers, A, B. So for example, the fraction 1/2 could be associated with the ordered pair 1, 2. Similarly, the ordered pair 2/7 would be associated, the fraction 2/7 would be associated with the ordered pair 2, 7. So, and vice versa. Any ordered pair I give you of natural numbers, you can make a fraction out of it, right? If I gave you, let's say, the ordered pair 3, 6, then you could produce a fraction based off of that. It would be, I don't need a parenthesis there. It would be 3 over 6. And so this is pretty neat. So we can think of fractions as like ordered pairs of natural numbers. And this relation, well, let's just investigate it. We know that the fraction 1/2 is equivalent to 2/4. Right? If we actually computed 2/4, we'd get 0.5, same as what we'd get if we did 1 divided by 2. So if we think of these as real numbers, 1/2 is like a real number, and 2/4 is a real number, they're the same. And we know another term for this is that they are equivalent fractions. So notice what happens when I multiply, well, let me write this as ordered pairs. So the ordered pair 1, 2 is equivalent to 2, 4. That makes sense in fraction language, but let's compare it to this relation we have here. Does it make sense for 1, 2 to be related to 2, 4? Well, let's check. Our relation, our formula that defines our relation is AD equal to BC. So the first coordinate of the first pair times the second coordinate of the second pair. So to check that, we would do 1 times 4, which is 4. Is that equal to, actually, maybe I should write it like this. I have a nice way to write this. So 1, 4, we'll multiply those together, we get 4. And then 2 times 2, we get 2. Or, we get 4. You're with me here, right? We get 4. And so in fraction language, right, we know that 1/2 is equivalent to 2/4. Converting that to ordered pairs, it should be the case that 1/2 is or 1, 2 is equivalent to 2, 4. And in fact, that's true in this relation. So what this relation is really doing, let me just rewrite it for a second. So we have AD, let me write it in white. We have AD equal to BC. Thinking of these as fractions, well, if I divide by D, on both sides and divide by b on both sides, I get AB equals C over D. So that is, these two fractions are equal if and only if they satisfy that condition. And if they satisfy that condition, then they are related. So this equivalence relation is really telling us about equivalent fractions, that two ordered pairs are equivalent if and only if the fractions that are associated with those ordered pairs are equivalent fractions. That's the idea. That's how to define equivalent fractions, is with this relation. So this is actually a very special relation. So let's move forward a slide. Let's check that this is really an equivalence relation, and then we'll maybe look at some equivalence classes. So let's check that that relation that I gave you on ordered pairs of natural numbers is really an equivalence relation. So how do we prove this? How do we prove that this is an equivalence relation? So I'll write proof here, and I'm going to divvy up my proof. All right, I need to show three properties. So let's first consider reflexive. So reflexive, I need to show that every element is related to itself. So I need to show that if A is in S, and actually we're talking about ordered pairs here, so I need to check if AB, an arbitrary element of n cross n, if AB is in n cross n, then I need to make sure that AB is related to AB, right? Every element of n cross n needs to be related to itself. So we'll do this for an arbitrary element so we can prove it for all of them. So let AB be an ordered pair in natural numbers cross the natural numbers. And let's check that it's related to itself. Then, so how can I do this? I want to see if AB is related to AB. So I'll multiply the first element, the first coordinate of the first pair, with the second coordinate of the other one. So that would be AB. And here I have BA. Then AB is equal to BA. So we can conclude then that AB is related to BA. Because that's what this condition means, is that AB is equal to BA. All right, let's check that it's symmetric. Remember here we have to prove that if two ordered pairs are related to each other, then they're related in the other direction as well. So assume AB is related to CD. So suppose we have two ordered pairs that are related, and we want to show, maybe I'll say want to show here, that CD is related to AB. So what does that mean for CD to be related to AB? Well, that would mean that I would need to show that CB. So that is, we want to show that, so first coordinate of the first one times the second coordinate of the second one. So we need to show that CB is equal to DA. Okay, but we're assuming AB is related to CD. So what does that give us? That tells us that AD is equal to BC, which implies, I mean, I'm just going to rewrite this a little bit differently, that CB is equal to DA, right? It's saying the same thing. I'm using here the commutative property of multiplication of natural numbers. And so that follows from that. Hence, CD is related to AB. So we just proved that it was symmetric. All right, transitive. So given given three ordered pairs. So let AB be related to CD, and let CD be related to, let's say, EF. We want to conclude, we want to show that AB is related to EF. That is, i.e., we want to show that AF is equal to BE. That's what we'd like to show. That would like to, if we can conclude AF is equal to BE, then we'll have showed AB is related to EF. What are we given? Well, that AB is related to CD. So what that tells us is that AD is equal to BC. And since CD is related to EF, we can conclude from that that CF equals DE. And so we're not quite there. We'd like to, right, remember, we'd like to conclude this, A times F is equal to B times E. So one thing I might do here, since I know I'd like to have AF equal to something, and over here I have A times D, what if I solve for D in this one, and then substitute that over in for D in the first one? So I have these two equations are true, and so let's try that. So CF equal to DE, well, that implies that CF over D is equal to E. I wanted to go the other way with that. CF over D, CF over E is equal to D. And so now I'll take that, D, and plug it in for D over here. So together, so AD is A times CF over E, which is also equal to BC. All right, where can we go from here? Well, I could cancel something out here. I have C's on both sides, so I'll cancel the C's out. This tells me, so this implies that AF over E is equal to B. And now what if I multiply both sides by E? AF equals BE. And there we have it. AF is equal to BE. And so that implies that we know that means that AB is related to EF, which is what we wanted to show. And so it's reflexive, we proved that, it's symmetric, we proved that, and it's transitive, we just proved that. Transitive was probably the hardest one of these, as you can tell, to show that it was actually transitive. And so we've shown all three, so I'll go ahead and end my proof. We can conclude then that this relation on ordered pairs of natural numbers is an equivalence relation. Hence, we'll have equivalence classes, and that gives rise to a partition. So I've mentioned this apparent fact that every equivalence relation gives rise to a partition. What I'd like to do now is go through a proof of that fact. And so this is sort of another level of proof, right? We're making, or I guess in the previous example, we just proved that something was an equivalence relation. Now we're proving a statement about all equivalence relations, that every equivalence relation gives rise to a partition. We'd like to prove a statement that basically says that. What I'm going to start with, though, this is going to be a lemma in our later proof, is the following theorem. If we have an equivalence relation R on a non-empty set A, and then A and B are elements of A, then the equivalence class containing A, so the equivalence class containing A is equal to the equivalence class containing B if and only if A is related to B. So that was that thing we saw in the example with the equivalence classes, that right, we looked at, say, the equivalence class containing 1, and we saw that 1 and 4 were in there. And then we looked at the equivalence class containing 4, and it was the same set. So compared to that, this is proving that that is true no matter what the relation is, so long as it's an equivalence relation. So independent of the set or the relation, so long as it's an equivalence relation, this fact should hold. So let's go ahead and prove this, that this will always happen. So this is an if and only if. So we need to show two directions. So I'll use my notation here, forward direction. So in this case, I want to assume the hypothesis, assume the equivalence class containing A is equal to the equivalence class containing B. And I want to show that A is related to B in this case. Okay. Well, let's think for a second. I want to show A is related to B, and I know their equivalence classes are the same. Okay. Well, it seems like this should be pretty obvious that this should be true, right? Because if I know if the element A is in the equivalence class containing A, and I know that equivalence class is the same as the equivalence class containing B, then I know A is in the equivalence class containing B, which means, by definition of equivalence class, that B is related to A. So let's go from there. So we know A is in this equivalence class containing A because R is symmetric. We know since, I'll write that down, we're using this, since R is reflexive. Since R is reflexive, right? Every element is related to itself, and so the equivalence class containing A contains the element A, since R is reflexive. Since the equivalence class containing A is equal to the equivalence class containing B, and A is in the equivalence class containing A, then A must be in the equivalence class containing B, because that's what it means for two sets to be equal, is that they have the same exact elements. So A is equivalence class containing B. Hence, by definition of equivalence class, B is related to A. And I'm done. Or am I? I want to show A is related to B. Remember that these do have an order to them. We're talking about ordered pairs. Of course, with an equivalence relation, we know that it's symmetric. So if B is related to A, then A is related to B. So I'll say since R is symmetric, A must be related to B. And so now I have the forward direction. For the backwards direction, for the converse, I will assume A is related to B, and I want to show that equivalence class containing A is equal to the equivalence class containing B. Remember that two sets being equal, I can show that two sets are equal if one is a subset of the other and the other is a subset of the first one. So that's equivalent to saying that A, equivalence class containing A, is a subset of the equivalence class containing B, and the other way around. B is a subset of equivalence class containing A. So if I can show these two things, I will have shown that those things are equal. So that's what we'll do. All right, so we know that A is related to B. I'm going to do this equivalence class containing A is a subset of equivalence class containing B first. So let's see. A is related to B, and we'd like to conclude. Right, so we want to show this subset. So let's give ourselves an arbitrary element of the equivalence class containing A. Let X be in equivalence class containing A. Then we know that A is related to X. Okay, so I have an idea of how we're going to do this. I'm going to flip this relation around from symmetry, so I know X is related to A. Hence, by symmetry, X is related to A. And then I know that A is related to B. Since A is related to B. So what can we conclude now? We have X is related to A and A is related to B by transitivity. X must be related to B. And so that's the same thing as saying B is related to X since it's symmetric. Therefore, that implies that X is in the equivalence class containing B. So we started with an arbitrary element of the equivalence class containing A right here, and we showed that it also must be an element of the equivalence class containing B. So it follows that A, equivalence class containing A, is a subset of the equivalence class containing B. Now let's go the other way. I'll call it Y. Let Y be in the equivalence class containing B. I'd like to show that it's in the equivalence class containing A. And I should be able to do a similar trick, I think. So Y is in the equivalence class containing B. That means that B is related to Y. I'm still assuming A is related to B. So I'm going to flip this around. I'll say by symmetry, Y is related to B. That lets me do that. Since A is related to B, remember that's our assumption for all of these. By symmetry, B is related to A. So we have that Y is related to B and B is related to A. So by transitivity, Y must be related to A. And that's the same thing because of symmetry, that A is related to Y, which implies that Y is in the equivalence class containing A. Hence, the equivalence class containing B is a subset of the equivalence class containing A. Since I have both equivalence class containing A is a subset of equivalence class containing B, and the other way around. So equivalence class containing A is equal to the equivalence class containing B. And I can conclude my proof because I've now showed both directions. We did the first direction up here, and the second direction we split into these two parts, this one, and we showed those each separately. And so that proved it, and so that's why. It's because, notice that we had to use all three properties for this proof to work. It needed to be symmetric so that we could flip these things around. It needed to be transitive so that I could, I don't know how to explain that. It needed to be transitive in order for these arguments to work, right? By transitivity, we had to conclude this. And it needed to be reflexive for this forward argument to work, right? In order to show A was related to B here, we needed to start with the fact that A was in the equivalence class containing A. So we really needed all three properties, and having all three properties was enough in order to conclude this. All right, so like I said, this proof, this theorem will be useful in the next theorem where I'll finally prove that every equivalence relation gives rise to a partition. So let's see that. So we are now finally ready to prove the following theorem that I've been talking about. Given a equivalence relation on a non-empty set A, if we collect all the equivalence classes, so if we take the set of all equivalence classes of A resulting from R, then that set is a partition of A. So let's think about what we have to prove here, proving this implication. So we'll start with the assumption that P is the set of all equivalence classes of A resulting from R. We want to conclude that P is a partition of A. So in order to conclude that P is a partition of A, well, we better remember the definition of a partition. So I'll say recall up here that P is a partition of A if three things have to be true. If A is in A, how do I want to write that? I want to say every element of A. I'll just write it in words. Every element of A is in exactly one element of P. So it's in exactly one set in P. And that every element of P is non-empty. So I need to conclude those things. Let's go ahead and start our proof. Actually, before we start our proof, I want you to remember what we proved in the last one, that equivalence class containing A is equal to the equivalence class containing B if and only if A is related to B. We'd like to use that at some point. Excuse me. All right, let's start our proof. So we'll start with our hypothesis, assuming our hypothesis. Let P be the set of all equivalence classes. Well, we've already seen that every element of A belongs to its own equivalence class. And that was from reflexivity. Since R is reflexive, A is in the equivalence class containing A for every element of A. Hence, I'll write it in words, every element of A is in at least one element of P. It's in at least one of the sets. Why do I keep drawing an R instead of a P? Of P. So it's in at least one of the sets, namely the equivalence class containing itself. Well, I don't want at least one. I mean, that's good, but I want to show it's also no more than one. So let's go by contradiction, and let's assume that an element of A belongs to two distinct equivalence classes. So let A equivalence class containing A and equivalence class containing B be two distinct elements of P. And I'd like to say that every element could only belong to at most one of those. And so let's suppose to the contrary that some element X is in both of those. Assume to the contrary that this element X is in A and X is in B. What does this mean? This means that A is related to X and B is related to X, but by symmetry, B being related to X means the same thing as saying X is related to B. So we have A is related to X and X is related to B. By transitivity, it follows that A is related to B. Now we get to use our previous theorem. We know that A is related to B, and so it follows that the equivalence class containing A is equal to the equivalence class containing B. So, by the previous theorem, A is equal to B. Now, why is that an issue? Because our assumption was that A and B were distinct equivalence classes. They were distinct elements of P. We were saying they were different, and we just showed that they're the same. this is a contradiction, what did this contradict? This contradicted the fact that we had an element in two distinct equivalence classes, right? We assumed these two things were true, and it led to this contradiction. This contradiction. So for all x in A, x is in at most one equivalence class. So we have it's in at least one equivalence class, and it's in at most one equivalence class, so it's in exactly one equivalence class. Those two together tell us every element is in exactly one equivalence class. That's this first bit. And actually that's the hard bit, because we also need to show that every equivalence class is non-empty, but that's what we would say is trivial because we know that R is R is reflexive, and so of course every equivalence class is non-empty because it has an element in it. But I'll say that down here. Since R is reflexive, for all A in A is in the equivalence class containing A. In particular, each equivalence class is non-empty. So these two together, right, these tell us that every element is in exactly one equivalence class, and this tells us that there are no empty equivalence classes. And that means we have a partition. And that's it. So this is going to be really handy in Chapter 7, which we're going to go to after Chapter 5, where we'll use this result to great effect, that we know that we get a partition from every equivalence relation. All right, see you in the next video.